And now let me crank up the presentation, which is here. And I'm gonna, there we go. I go into slideshow.
Oh, okay. Yeah.
Okay, do you see this?
Yeah.
This is an idea I had that basically in the 19th century, there was a huge amount of work in classifying elements. And this resulted in this thing down in the bottom left called the periodic table of elements. And it suggested there was a huge amount of order there, but no one knew, what it was. And then in the early 20th century, especially the 1920s, there was a lot of activity to create something called quantum mechanics, which dealt with discrete energies. And that went a long way toward explaining the order that underlies this periodic table of elements. So, and that in turn led to things like the transistor and to the laser and a lot of the stuff that we have today in our phones and computers. So, huge change. So what's happened is I got in the top right here a periodic table of finite simple groups. So what's happened is that mathematicians have been working on studying symmetries, patterns of symmetries, and they, after literally 150 years, they came up with the characterization of 20 different categories of symmetries. But then what was crazy was there's 26 down at the bottom, 2 rows of 13 each, exceptional or sporadic types of symmetries that don't fit into the 20 categories that are up above here. But there's clearly a huge amount of order here, just like with the periodic table of elements. But this deals with space. The symmetries we're talking about here deals with space and in many dimensional space where all these symmetries are occurring. So what I anticipate happening in the next, period of time is that people will figure out the reason for why we have this symmetry in space, what's causing it, and that'll lead to a similar revolution like we had once we did quantum mechanics coming out of the periodic table. So, let's see if we can remotely begin to do this. So we start here, the periodic table of elements. The basic idea is that all matter is made up of atoms, but the atoms, while they're discrete, are all different. There's what's called an atomic number, which is the number of protons in the nucleus of each atom, or the number of electrons in this cloud around the nucleus. And you have to remember that the size of the atom, we went through this before, if I looked at the nucleus and had it sitting there on the altar in St. Peter's in Rome, in the Vatican, it's sitting there on the main altar, then the size of the atom where the electrons are would be equal to the size of the Basilica of St. Peter. So there's a huge amount of empty space there with the electrons running all over the place around this nucleus. Another thing to keep in mind is that there's recurring patterns here in this periodic table. We can see there's columns and rows, and when we go across a row, we end up with things going from very, I'll just say active or acidic to things that are very basic or very negative, and then it repeats. We go down the next row across, and this repeats. So there's this huge amount of symmetry here, which over time, over decades, led to this mathematical physics theory called quantum mechanics. Now, again, the same thing is true here for the study of the symmetries in space in many dimensions. And there's 20 basic families of these symmetries that are captured here in these columns. There's 20 columns here. And then there are these 13 times 2 or 26 exceptional or sporadic families of symmetries that themselves don't lend to any categorization. But probably this is going to lead to some amazing linkage between mathematics and physics. We just don't know what it is. So the periodic table of elements has elements in rows, which are called periods, and then columns that are called groups. And it's periodic in the sense that it repeats. So when I run across a row and then drop down to the next row, the pattern, the properties repeat here. And there's roughly 4 rectangular areas or blocks that make up the periodic table. We'll come back to that. And if I start on the left and go down, things get more and more metallic. And I go from right to left, they get more and more metallic. And they're non-metallic, increasing going from the bottom left up to the top right, just to characterize what's going on. So all of this, there are many people working on this, but one person who ended up making predictions out of what he saw that turned out to be true was Dmitry Mendeleev. And he when he was doing this in 1869, not all these elements were known, and he used this periodic law to predict properties of, it was 3 different missing elements. So it was a huge, that when they were, each of those 3 was discovered, people recognized that Mendeleev was onto something, and this ended up being the periodic table of elements that we have today. So in nature, we only have up to number 94 that exists, and we can go further than that, but they have to be synthesized typically in these particle accelerators. So by 2010, there were 118 elements known, so 94 in nature, and then the rest were all synthesized. 18 plus 6 is 20. But the problem with this is that just because you've created a small amount of one of these elements, you really don't know anything about its chemical properties and so forth. So there's still going to be new discoveries in the periodic table that are going on and so forth. Each chemical element has a unique atomic number. Since the Germans are so active, the atomic number is called Z, which is Zahl in German for number. And so we have atomic number 1 is hydrogen, atomic number 2 is helium, atomic number 3 is lithium, and so forth. And these atomic numbers are called chemical elements, and so it goes. So we also end up having letters for these things. So we use H for hydrogen, He for helium, Li for lithium. There's typically one or two letter abbreviations, which, as you can see in this table here. The neutrons don't affect the chemistry. It's really the electrons that control the interaction between atoms. And then we have the fact that atoms, the same number of protons with different number of neutrons, are called isotopes of the same chemical element. We always focus on the number of protons, which equals the number of electrons. So we've got naturally occurring elements occur as mixes of different isotopes. And we don't know why there's a mix of these things, but there is, probably for each of these elements. So hydrogen has three different isotopes. The one we're familiar with is there's a single proton and a single electron, but which is called hydrogen. But the first isotope is deuterium, which has one neutron to go with one proton and one electron. And then we have tritium, which has two neutrons and one proton and one electron. So even hydrogen, leads to some interesting things. The reason for focusing on hydrogen is it's the simplest of all the elements. And quite frankly, even with quantum mechanics, it is the only one that people have worked out analytically all the different possibilities for where the electrons could possibly be in a hydrogen atom. Once you go to something like helium, it's hopeless to actually do this analytically, and you have to do everything with numerical methods where you approximate what's going on. And there's a lot of movies, videos on YouTube showing what these things look like. The isotopes are never separated in the periodic table. They're always grouped together with a single element. So when an atomic mass is shown, it's usually the weighted average of all these naturally occurring isotopes. And so it goes. So in the standard periodic table, starting up on the top left and moving down to the bottom right, the elements are listed in order of increasing atomic number. And every time that we have a new row, what that means is there's a number of electrons that have completely filled up all possible configurations in what's called the shell. And therefore, the new row starts off with the shell underneath it completely filled, and it adds one electron. And then you continue to add them as you move across the row. And the elements within this have different properties. But for example, if we focus on a column would be where we have here's oxygen, sulfur, and selenium. They all have 4 electrons in their outermost shell. That's all that there is. So elements with similar chemical properties fall into the same group. But it gets to be more and more complicated. There's a lot of, I'll just say, art associated with this stuff. The 24 artificial elements start elements 95 to 118 occur only in these laboratories. Of the 94 naturally occurring elements, 83 are found in nature, and 11 occur only in decay chains of these 83 primordial elements. So some of these are so rare that they weren't discovered in nature. They were synthesized in a laboratory. So we have this element 43 technetium, or promethium, element 61. But these actually did all exist in nature. People just missed it. Going on up to plutonium, which is close to the last one we're going to find. So no element heavier than element number 99, which is called Einsteinium, has ever been observed in any sort of macroscopic quantities. And the element number 87, francium, has only been photographed in the form of light from about 300,000 atoms, which is nothing. So you can see this is an amazing experimental tour de force to go deal with these things. There are 80 stable isotopes out there, and there's others that have stability of, for example, 10 to the 19th years, which is over 1 billion times greater than the age of the universe. So, you know, you're saying that it's not stable, but if it's 1 billion times more stable, has a half-life over the age of the universe, or half-life means you sit there and watch it decay until it gets down to just half of what you started with. It's the time scale's incredible. And so it goes. So of the 94 natural elements that we talked about, that's it. Yeah. There's an international naming convention, so that the groups are all numbered from 1 to 18 in the leftmost column, which are called alkali metals. And when we get to the rightmost column, which is this yellow one here, these are the noble gases. And so it goes. For reasons of space, the periodic table is commonly represented. There's a middle. If we stretched it out here, this is the natural way to show it, so that there's 4 groups: 1, 2, the blue one, the green one, the red one, and the orange one. But this goes out this way a long way, takes up a lot of space. So typically what people do, let me get this out of the way, is they rearrange it. So the blue one, is still here. The red one that takes up all of this space here gets put down below into this thing. The green one is still floating around here, and so it goes. So the basic idea is just how can you convey all this information so that people can understand it. These periodic tables end up showing a lot of supplementary information with color coding or data or whatever, and the names and atomic numbers of the elements are in there, what block they're in, their atomic weights, etc. So an electron can be thought of as inhabiting an orbital or a space around this nucleus, which characterizes the probability it can be found in any particular region around the atom. But these energy levels are quantized or discrete, so they can only take on discrete values for these electrons. And the electrons obey this Pauli exclusion principle that different electrons must always be in different states. No 2 electrons can be in the same state. And so this allows the complete categorization of the different energy levels, which are called shells, that are divided into subshells and so forth. They're called orbitals because you think of them as running around or orbiting the nucleus, but they're really not orbiting in any sense. They're in a cloud running around because they're running so fast you can't really stop them, except what Ron Cowan did. He was able to stop them and see something happening. Each orbital that we're dealing with can have 2 electrons, and the thing is that the electrons have a quantity called spin, which is labeled as either up or down, and so therefore we can get 2 electrons, 1 for up, 1 for down, into each orbital, and so it goes. the elements are known up to the first 7 shells that are occupied. And the first shell is called the 1s orbital, and it can hold up to 2 electrons. So hydrogen has 1 electron, helium has 2 electrons, and those fill the first orbital, the first 1s orbital there for the electrons. When we go to lithium, it similarly got a 2s, not a 1s, a 2s. It's the second row orbital, but it can have 3 p-shaped p orbitals, and they can each be up or down. So in 3 directions, X, Y, and Z. So I end up with 2 electrons in the 2s orbital, and 2 electrons in each of 3 of these p orbitals for a total of 8. And the rule of 8 is what triggered everything in the periodic table. So the second row is 8 across. The third row, we now start over again. We have a shell with a 3s orbital. So we have 2 electrons there spinning up and down in the 3s orbital. We have three p orbitals, just like we saw before. So now we're up to 8. But then we end up with 5. We went 1, 3, 5, 3d orbitals. So now we end up with 18 total, which is why this is 18 across, not 8. The fourth shell contains 2 in the 4s, 2 in each of the 3 4p's, 2 each in each of the 5 4ds, and 7. So we have 1, 3, 5, 7. So this leads to a capacity of 32, and so it goes. So here's a little picture to try and capture that. You end up with this s orbital being here, and there's always just at most 2 electrons in that. And the capacity here, there's this number that's showing up here at the top, which is due to angular momentum, which I'm not going to go into right now. But then there's 2 occurring there, 8 occurring here, because we've got 2 here plus 6 here. It gives me 8. And then we have another 10 here, takes me to 18. And then we have another 14, which takes me to 32, 50, and 72. And so you see, it takes me up to element number 98 when we have this many things going on. So what I thought I would do, I'm going to just do a little bit more, and then we're going to switch to a YouTube video. So we've got discrete mechanics or quantum mechanics, where we have an electron in a single state. And what this leads us to is when we have multiple electrons, the electron cloud has an angular momentum, which is different from the spin of each of the electrons, because the cloud itself is spinning. And the more electrons, the greater the angular momentum, but you only get certain values. Now, what happens, what's surprising about all this is when I was a student, we had a whole class on solving certain classes of ordinary differential equations. And these equations had interesting things called special functions that solve particular categories of these equations. And the equations typically arose out of physics or out of some astronomy type application. But there was, for example, astronomer Bessel, who ended up developing what are called Bessel functions today, or Legendre, who developed polynomials that were a solution to his category of things, or Hermite, who had polynomials that were here, and so forth. See, these are all special cases of what are called hypergeometric functions, which are, they all have names and they're useful for solving particular problems. But what's interesting about these is they have these same numbers that we just talked about: 2, 6, 8, 10, 14, 32. They all come out of these ordinary differential equations solutions here, these special functions. And these things are used all over the place. And they have another interesting property to them, which is when you actually look at these things in this space of functions, they're all perpendicular or orthogonal to one another. So you can use some type of Fourier analysis to look at the actual solution you're dealing with, and so it goes. So let me break out of this. Hold on, I'm gonna stop sharing here, and I'm gonna go back over here. And there's this really energetic guy here. You'll see in a second. Oh, wait, I gotta get the, wait, I forgot to get the sound. Hold on. Sound share, here we go. So this guy's got a very popular YouTube channel. Here we go. Gonna go back to the beginning here. And we'll see how he
Professor
does.
Dave here. Let's learn about quantum numbers.
Hold on one sec. I forgot one thing. I was listening to these things at twice speed.
Now that we understand that electrons are both particles and waves, we are ready to learn about how electrons are arranged in an atom. The location and energy of every electron in an atom is determined by a set of 4 quantum numbers that describe different atomic orbitals. An orbital is a region of probability where an electron can be found. There are s, d, p, and f orbitals with different shapes, and they look like this. Remember, these shapes are not electrons, just regions in space where electrons can be, and each one can hold up to 2 electrons. The more electrons an atom has, the more of these orbitals it will need to accommodate them all. The first quantum number is the principal quantum number n, which can have any positive integer value. We saw this when we learned about the Bohr model. It represents the energy level of the electron. Each orbital will have an n value, and the larger the value of n, the further away from the nucleus it is. The next quantum number is the angular momentum quantum number, L. This can have any value from 0 to n-1. For example, if an electron has an n value of 3, it can have an L value of either 0, 1, or 2, because 2 is 3 minus 1. The L value describes the shape of the orbital. When L equals 0, we are describing s orbitals, which are spherical, just one of these per energy level. When L equals 1, we are describing p orbitals, which are lobes that extend outwards on 3 axes. There are 3 of these per energy level. When L equals 2, we are describing d orbitals, which are weird looking, 5 of these per energy level. And when L equals 3, we get f orbitals, which are even weirder looking, 7 per energy level. Next, we have the magnetic quantum number m sub L. This can have a value of anywhere from negative L to L. So if L is 2, m sub L can be negative 2, negative 1, 0, 1, or 2. This quantum number determines how many orbitals there are of a type per energy level, and therefore describes a specific orbital amongst a particular set. When L is 0, m sub L must also be 0, and that's why there's only one s orbital per energy level. When L is 1, m sub L can have 3 values, which is why there are 3 p orbitals per energy level. An L value of 2 gives us 5 values for m sub L and 5 d orbitals, and an L value of 3 gives us the 7 f orbitals. The last quantum number is an easy one. It's the spin quantum number, m sub s. This one will be either 1/2 or negative 1/2, no matter what. So every electron in an atom has a unique set of quantum numbers. No 2 electrons in an atom can have precisely the same 4 quantum numbers, as is stated by the Pauli exclusion principle. This is because any orbital can only hold up to 2 electrons, and even the 2 electrons in the same exact orbital will have opposite spin values. So let's try to describe different sets of quantum numbers and what they mean. When n equals 1, L must be 0 and m sub L must also be 0. That means we are describing the 1s orbital. It can accommodate 2 electrons, which will have spins of half and negative 1/2 respectively. This is the lowest energy orbital, so any atom on the periodic table will fill this orbital first. The electrons in hydrogen and helium occupy this orbital since they have only 1 and 2 electrons respectively. When n equals 2, L could be 0, which would give us the 2s orbital, or L could be 1.
This February at Renewal by Andersen, replace your windows, your patio doors, or your entry door.
Be 1, meaning m sub L could be negative 1, 0, or 1, giving us the 2p orbitals. The outermost electrons in the second row of the periodic table will occupy these orbitals. When n equals 3, L could be 0, giving us the 3s orbital. L could be 1, giving us the 3p orbitals, or L could be 2, giving us the 3d orbitals. A large atom will have to use all of these orbitals and more to house all of its electrons. The Aufbau principle tells us the order in which an atom will fill up its orbitals. This is determined by their relative energies. Orbitals that are further away from the nucleus have higher potential energy, so it'll be 1s first, then 2s, then 2p, 3s, 3p, and so forth. We can use this to determine the electron configuration of any atom. For example, a neutral chlorine atom has 17 electrons. So looking at the orbitals, each of which can hold 2 electrons, let's fill them up starting at the lowest energy and then climb upwards. The 1s orbital gets 2 electrons, one spin up, the other spin down. Then the 2s, then the 2p's, then the 3s, and the last 5 will go in these 3p orbitals. Hund's rule says that for electrons of the same energy, you put 1 electron in each orbital first before doubling them up. So 1, 2, 3, 4, and 5 gives us a total of 17 electrons for chlorine. That means chlorine has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p5. The numbers before the letters are the n value for the orbital. The numbers after the letters tell you how many electrons sit in each type of orbital. If you want a quicker way to determine electron configurations, just know which areas of the periodic table correspond to which types of orbitals. This area is called the s block. This is the p block, here's the d block, and then the f block. When we are determining the electron configuration for an atom of a given element, the easiest way to do it is just travel left to right and up to down on the table until you get to the element, since each element has one more electron than the last. Looking at chlorine again, the top row is just the 1s orbital, that's full, so 1s2. Going to the second row, where n equals 2, we fill the 2s orbital, which holds 2 electrons, hence 2 elements, the 2p orbitals, which hold 6, so we pass 6 elements. Then the next row down, we fill the 3s orbital. And lastly, we get to the 3p's and count 1, 2, 3, 4, 5, 3p5. A common abbreviation is to use the noble gas from the row above and list it in brackets. This would be read as neon core, and it implies the ground state electron configuration of neon. Then you just list the valence electrons of the element, or the ones that correspond to the row it is in. We can use orbital diagrams to visually depict how the orbitals are filled, and they look like this. Don't forget Hund's rule, fill each set halfway before doubling up. For a quick definition, atoms with unpaired electrons in their orbital diagrams are called paramagnetic and are attracted by a magnetic field. Atoms with all of their electrons paired are diamagnetic and are not affected by a magnetic field. So to summarize, n tells us the energy level, L tells us what type of orbital, m sub L tells us which specific orbital amongst a set, and m sub s tells us the spin. Each electron in an atom has a unique set of quantum numbers, and an atom will fill up orbitals with electrons according to the Aufbau principle until all of its electrons have a place to stay. This is a tricky concept, so if you feel confused, try watching one more time from the top. Otherwise, let's check comprehension.
So for example, L is 1 here, that's impossible. uh, the spin never can be 3 halves. We see ML must be minus, L is 1, so this must be -1, 0, or 1, not 2. And then N always has to.
Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Let me see if I can spell that. Hold on a second. Easier said than done. Oh, here it is. Okay. So I'm pretty well. Let me see how I can get rid of this. Well, here it is.
Professor Dave here. Let's learn about quantum numbers. He knows a lot about the science.
Okay. Now let me go back to the presentation. So I'm just trying to give you a taste of what happened in the 1920s with quantum mechanics, and it led to this, I'll say, higher level understanding, but it doesn't really explain why do these special functions and these integers come about in the way that they do. It just gets presented to you as a set of rules, and quite frankly, things haven't progressed much since then. So let's see. Why doesn't this thing want to, there we go. So we saw there's 4 numbers, and the 4 numbers were the energy level, 1, 2, 3, the angular momentum, 0, 1, on up to n-1, where n is the energy level, the magnetic number, which goes from -L to L, and here's L over here. This is, and then finally the spin, which is +1. So there's 4 numbers, and it captures everything. Having said that, I just got through saying that the only solution we have for this is for hydrogen. All of these other things, we have no, I'll just say, analytic methods to do anything with these. So it's all done numerically. And there's a lot of YouTube videos showing what all these electron clouds look like for each of these different elements. And the chemists are busy playing with this night and day. So the thing we talked about was having these shells or orbitals, and we start off with 2 in the bottom shell. There's always 2 in the bottom shell. So we have just these things here, and then we go up to the 2nd level, 3rd level, 4th level, and you can see how it goes. So this is, on the one hand, it's a great accomplishment. On the other hand, it leads you to all kinds of questions like, where in the world did this come from? What else is new? And I put a lot of stuff in here, but I decided to just basically skip over it because there's a huge amount of playing around with all these different numbers to get somewhere. The key thing to keep in mind is that the size of the atoms are dependent on the size of their outermost orbitals, where the electrons are, and they generally decrease going from left to right across the periodic table because the nuclear charge increases, but the outer electrons are basically all in the same shell. But if we go down a column, then the radii of the atoms generally increase because the outermost electrons are in higher shells and are thus further away from the nucleus. So you end up with things like this. And thing to keep in mind here is that this is very useful for chemistry, for trying to come up with properties of different things. So, for example, there's a lot of activity right now with batteries and trying to understand how to come up with batteries that have an ideal set of characteristics, and this is used night and day by those people to come up with those things. The history of all this, we're just going back in 1817, a German physicist, Derbrunner, began to formulate how to classify the elements, and he came up with what he called triads, or groups of three. So chlorine, bromine, and iodine formed a triad. Calcium, strontium, and barium formed a triad. Lithium, sodium, and potassium formed a triad. Sulfur, selenium, and tellurium formed a triad. It was a great start, and people started to build on this, but they wanted to come up with one scheme. And there's a big push here with this guy, John Newlands, about the periodicity that's going on. Then there was another German chemist, and he published a book showing what's going on. But it was really Mendeleev was the one who really came back. He started February 17th of 1869. He began arranging the elements, looking at their atomic weights, etc. And after he found a consistent arrangement, he printed his table, but it was in the Russian Chemical Society, so it didn't really get a lot of play, for example, in Germany or France. And when elements didn't appear to fit in the system, Mendeleev predicted that there would be elements that would fit there, or existing elements had been improperly characterized. They had the wrong atomic weight, the wrong number of electrons, or that there was a missing element. And that was what made it for him. And so in 1875, this French chemist, Baudron, working without any knowledge of what Mendeleev had said, found a new element, and he called it gallium. And he couldn't believe that Mendeleev had predicted this. But after he started looking, he saw that Mendeleev was indeed correct. In 1879, this Swedish chemist discovered a new element, but that turned out to be a type of boron. And in 1886, the German chemist found something which was called germanium, and all of those matched. Gallium, scandium, germanium matched exactly what Mendeleev had predicted. So because of this, Mendeleev won the prize. In 1913, this Dutch physicist proposed that the nuclear charge really, or what is now called the atomic number, or Zahl, Z, determine the placement of the elements in a periodic table. So every time you see a number there, 1, 2, 3, 4, 5, that's how many protons there are, or how many electrons there are with that particular element. And Rutherford coined the word atomic number for this nuclear charge, which is different than atomic weight, because the atomic weight includes the number of neutrons as well as the number of protons. And so in 1914, Rutherford did all this work, and it was accepted by people, and the rest is history. There was a lot of X-ray spectroscopy going on. There was all kinds of push to determine the protons and then the number of neutrons in there. There were missing elements that all were discovered, even though they didn't realize it. And all of this led to the clarification of what an isotope was. You can have different number of neutrons with the same number of protons in the nucleus. And so the term isotope was used to describe the situation. The thing was that apparently Annie Besant and Charles Leadbeater, who published this book, Occult Chemistry, in 1908, they were the ones that first came up with this notion of isotopes, and Soddy just picked up on it. And so a lot of these experiments that led to the creation of the periodic table of elements led to this notion of discrete energy levels and spins, and this led to what is called quantum mechanics, which we just got a touch of, seeing all these integer numbers flying all over the place. And this led to the ability to engineer materials that we use today in our phones and computers. And increasingly we use light rather than electrons. But all of that is due to this area called quantum mechanics. So let's just flip over now to the math side. So in math, the study of symmetry leads to a structure called a group, or a group theory that studies algebraic structures known as groups. And this is really central to mathematics, the study of symmetry. And as we'll see, and when we look at, for example, crystals, or we look at these different atoms that are there and the different orbitals they have, there's all kinds of symmetries that come out of these things. And this ends up being a very powerful tool to characterize everything. So the thing all started in the 19th century with Galois, who created the initial major work, and it was picked up, and really in the 1970s and 1980s, people started to see what was really going on, but it really was only until the year, say, 2004, and there are 10,000 pages of journals articles that gave a complete classification of all of these types of symmetries that could be there. And the problem with this is that you're dealing with number theory, the theory of numbers, you're dealing with the theory of algebraic equations, and you're dealing with geometry. So this runs across all these different things. And this is all clearly related to the study of space itself. What sorts of spaces have what sorts of symmetries? I mean, if I'm in a three-dimensional space, I have a certain set of symmetries. If I'm in a 24-dimensional space, I have many more possible symmetries. And so many mathematicians worked on this in all kinds of different activities. Galois actually was able to show, by using the study of symmetry, that it was impossible to come up with a solution to a fifth order algebraic equation, something of x to the fifth plus something times x to the fourth, and so on. It was impossible to come up with any sort of analytic solution. People had come up with solutions for first order where x squared, x cubed, x to the fourth, and they were just working away on x to the fifth. It never crossed their minds. It was impossible. Galois showed it was impossible. And anything higher than 4 is impossible. But it was all due to framing it in a totally different way, looking at the symmetries that were arising from these things. Then having said that, we end up with the most simple example is a permutation group. So suppose we took 3 numbers, 1, 2, and 3, and we wrote them out 1, 2, 3. Well, we could write it also out as 1, 3, 2, or we could write it out as 2, 1, 3, or we could write it out as 3, 2, 1. So we have a set of permutations of these numbers. And having done that, there's a possibility for all of these different permutations that we come up with. We come up with certain patterns that are possible and certain that aren't. And that's what Galois observed, was that when you started to go for things with 5 or more entities, 1, 2, 3, 4, 5, you couldn't do anything in algebra in 5th order equations. So that's what really drove everything. And then there was an activity dealing with matrices, or rows and columns of numbers. So anytime you deal with this, there's some type of action that takes place that transforms a vector in an n-dimensional space to a vector in the same space, but with different dimensions to it. And the action of all this stuff is very useful for discovering the properties, symmetry properties here. And that led to more and more activities here to come up with all kinds of different things. And so the thing that has happened here with this is that there's a set of groups here that are captured here. There's 20, 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and then there's 2 more up here that I skipped over. Okay, total of 20. But down here at the bottom, we have 3, we have 13 here, and another one of 13, a total of 26 that don't fit in anywhere. And that's just the way it goes. No one understands why this is the case. Just like in quantum mechanics, no one understands why do these magic integer numbers occur all over the place to describe these energy levels. It just is the way things work in the universe that we're in. And so what Ron Cowan found was we have actually 24 spatial dimensions and 2 time dimensions. Here we have 10 dimensions for matter, 9 spatial and 1 for time, and dark matter had 1 for time and 9 for space. And these are perpendicular to one another, but they're linked by this other set of dimensions up here at the top, this other 6-dimensional space. And there's holes that interconnect these things. So the power of this is that these 26 exceptional or sporadic groups link to each of these 26 dimensions that we have here, except that that's a conjecture. We don't know that that really is the case, but it seems to me make a lot of sense. But why is that the case? And what goes with it is this other thing that Ron observed about information controlling everything, that everything in the universe around us is coded with the blocks of information that are constantly scanning the world around us for change. And this information is being shared. Well, probably what happens with the information being shared here is that the information is shared outside of the 26 dimensions that we have. That is, for everything to couple to everything else, if I step outside of my 26-dimensional space back here it is, I step outside of it, then I can step back in anywhere and link it to it. And so probably what's going on here is we have to understand the space that is around our universe that itself has no meaning. There's no space there, but that's where this information gets shared apparently, and it's an amazing accomplishment. So with that, I'm going to quit, and we're going to hope and see what in the world do people come up with for we're right on the verge of doing something with all of this geometry, but what it is, I don't know yet. And all we saw what happened in quantum mechanics was people found a whole bunch of things that had already been discovered in the 19th century for what are called special functions that led to these integers, 1, 2, 3, et cetera, for the characterizing the solutions of these equations. I don't really view that as useful, but it's the state of where we're at right now, is that this is what we know, and there's going to be something else that'll happen with symmetries that will lead us to a much deeper understanding of space itself. That's what the symmetries are dealing with, and also time, because I said 2 of the dimensions were time, and we'll end up with some amazing engineering taking place. We'll have anti-gravity, and we'll have time travel, and you name it. But that's not for today. That's where we're at.
What we need is our 10.
Go out there as a discussion, Bruce. Any comments?
Yeah, I was just saying, like, what we need is our 10 meditators like Ron.
Yeah. Yeah, and they checking each other and pushing each other.
Yeah,
And then you'd end up with something meaningful. But he was pointing in the right direction, okay? And it was with his ties to Emmy Noether there that led to all this. And I think it's a very powerful set of insight, because if you don't know where you're going, any direction works.
right.
You got to have some idea, what in the world does the answer look like anyway? And it's not obvious that it should be 26 dimensions, 2 of which are time and 24 is space, but that's what Ron saw. So
Right. Well, the thing is that he had insight and awareness in his own mind of these levels of reality.
right. And he'd been around. He's an old soul. He'd been around.
Yeah, he's an old soul, right?
Forever, and so he learned a lot, and we're just trying to stimulate other people to look at what he did, to try and see what are the linkages here, and he could very well be onto something, but we'll see. Too soon. I just thought this would be a fun thing to stick in here, because having this periodic table of elements really led to the physicists going crazy, and creating quantum mechanics and so forth. And here the mathematicians have done the same thing, probably more difficult than what the physicists did, and yet we haven't begun to really mine it for what this really means. We're right on the verge of doing that. So the next several decades, there'll probably be some amazing advances that occur, but what they are, I don't know. So anyway, that's it for tonight. Have a great time. Have a great weekend. We'll go back next week. Have a good. Okay. Bye-bye.
Right.